ready to start? Welcome to this module on optimal power flow. So today and the following weeks, we will discuss controlling the grid and using optimization technique, adding optimization to the modeling that you have seen in the past weeks. We'll do it in two parts for the optimal power flow. This is this week, this is next week. So optimal power flow is really the canonical grid control problem. So that's the standard problem that any grid control system has to solve. It's formulated as minimize the cost of operation of an electrical grid subject to constraints. What are the constraints? Well, the constraints are on grid operation, on voltage, for example. The voltage should be within plus or minus 10% of 1 per unit of the nominal value. This is to prevent malfunctioning of devices. When the voltage gets very high or very low, many devices will have problems. So that's one of the quality of service constraints. Another quality of service constraint is the current in the lines and in the transformers. If the current gets too large, the lines will heat and the insulators might get destroyed. So those are the typical constraints on the grid operation. The control variables, what are the things that you control? Well, it is, as we will see on an example, very typically the generators. How much does each dispatchable generator generate? And then you have a number of other devices like batteries. In the lab, you will see examples where a battery can act as a generator, but also as a sink to absorb energy, and a number of other more discrete operations that may change the qualitative or quantitative behavior of the grid. For example, what is called tap changers. Tap changers are discrete settings in the transformers that can change the output of a transformer, the output voltage, from one value to the other. So this is what the problem is. It is used for, I mentioned control. Control is used for different time scales. The very classical one, the one that is used every day, that enables us to receive electric power without problem now, for example, is for planning the grid, for deciding which generator in Switzerland, but more generally in continental Europe, has to generate and how much in order to satisfy all those constraints here. We will see also in the labs how to use this for operation of the grid. A motivation is when we have a large penetration of stochastic resources that are, for example, solar panel. When we have a lot of solar panels in a grid, we see problems of overvoltage at those periods of time where there's a lot of generation. Typically now, at this part of the year, between now and September, around the middle of the day, the solar panels will generate much more than in average. That may cause overvoltage in some parts of the grid, and that needs to be taken care of. You may have the converse problem if you have a lot of loads. For example, electric vehicles that may be very large loads. When they get connected to the grid and they all pump energy at the same time, that may cause undervoltage. That needs to be taken care of. That can be taken care of by, for example, having batteries in the grid that will inject more power at the time where the electrical vehicles are using it, or absorb more power at the times where the solar panels are generating in excess here. That's examples of operation of a grid. Here's a toy example that I will use in this lecture to illustrate the technical concepts that we will use. So this is a grid with 3 buses, 1, 2, 3. 3 at the buses are connected generators. Those are the round objects here, and loads. Those are the arrows here. And let's assume we have the following planning problem. So we are the manager of this grid, and we need to do the planning exercise. Planning is done by markets and also by what is called the grid, the system operators in Switzerland, Swiss Grid, that has to decide at several time scales. But let's say, for example, every day, 1 hour before real time, so 1 hour before now, Swiss Grid had to decide what is the set points of all those generators. Swiss Grid did not decide to every company how much they will generate, but they let first the market decide. So every We will discuss that in 2 weeks, how the market can come to play. And once the different actors have decided how much they think they will generate, then you typically need a few additional reserve generators that will make sure the system is completely balanced. That's the true story. Now, in this simplified example, I'm assuming I have full control of this grid, and I need to set up the values of those 3 generators here. This is, for example, the case of an operator like Romande Energy that would have a small grid that they control here. Those 3 generators have different capabilities, which are expressed here. They have minimum and maximum active power, 400 megawatts for all. Also maximum and minimum reactive power, 80. And importantly, they have different costs. So generator 1 has a cost of 15 francs per megawatt hour, generator 2, 1 franc per megawatt hour, and generator 3, 225. So G1 is not so expensive, G2 is inexpensive, cheap, and G3 is very expensive. Now, if there would be no grid and you need to optimize the system, you have to serve the loads. So the loads are indicated here. So based on some forecasts, for example, this operator thinks that there will be 100 megawatt consumed at bus 1, 100 megawatt at bus 2, and 500 at bus 3 here. So we have to serve 700 in total, and we have a capacity of 3 times 400 here. So if I have no constraints on the grid, I would, of course, use maximally the cheapest generator. So I would generate 400 megawatt here, then 100 megawatt from this, and 0 from that. That's what I would do if I had no grid. But I have a grid. The grid, which is the essential problem we're discussing this week, has a number of side effects, 2 essentially. First, there are capacity limitations. Here, the grid is not able to sustain any arbitrary amount of power. That's really the bottleneck in the interconnected electrical system of Europe now. You have those high voltage lines, as you see in the landscape. They're not very beautiful, but they're very useful. And they have limited capacity. And augmenting the capacity means building another line, which is an effort that will take many, many years. And also people don't like to see lines, so there's a lot of resistance against lines. So that's really a bottleneck in the system. That's the capacity of the lines. Here I'm assuming the lines here have a capacity that is expressed in apparent power, 300 megawatt for each of the lines, except the line 1-3, which has less capacity, 200. So this one has 300, 300, and 200. So that's a first limitation that we'll have that will make my solution impossible here, because I will not be able to have 400 here that flows there to feed this demand of 500 here. That will not work. That's the first implication of having a grid. There is another implication, which is that the grid is not exactly transparent. If I inject 500 megawatt here, well, I cannot, because if I inject, let's say, 200 megawatt here, what will come out here will be a little less than 200 megawatt, because there will be losses, thermal losses due to the resistance of the line. And also there might be also voltage problems, because the grid is not just shuffling active power, but there's also reactive power that influences largely the voltage. So there are also constraints due to voltage and to the presence of reactive power here. So if we want to account for all this, we need to pose an optimization problem, which in this case could be in this way. If my objective is simply to minimize the total cost, I have to control G1, G2, G3. So my control variables, the values that I need to decide by my optimization problems, are G1, G2, G3, plus a number of other variables that are nuisance variables. They are variables I'm not really interested in, but they exist in the physics of the system. Those are the electrical state of this grid, which, as you have seen in the past week, is given by the complex voltage at all the nodes, from which we can deduce the values of the power flows on all the lines. So I add all those variables into the constraints, and I may add constraints on the voltage magnitude, on the intensities on the lines, and perhaps also on the branch flows. Sometimes I have only one of the two constraints, but in general, let's admit to, and also constraints on the generator limits, the capabilities of the generators here. So if I put all of this together, for example, for this example here are all the details. I need to add variables for the electrical state of the grid. Here I add the complex voltage. I also introduce auxiliary variables of the complex line flows and the complex power injections at each of the nodes here. Now, this is the grid, the load flow equations in rectangular coordinates, where the star means the complex conjugate. So this is expressing the injected power at bus 1, which is equal to the voltage at the bus, the complex voltage, times the conjugate of the current, and the Y is the admittance matrix of this grid here. So that gives the first equation. Then to simplify here, I'm assuming that the angle of the power generated by those generators is also a known variable, phi. So that gives me what is the apparent power as a function of the, this is the complex power generated by the generator here. I'm assuming those generators can play with both dimensions of the power, active and reactive. And I'm assuming that the load has a known cos phi, a known angle here, which means the active power consumed by the load is Li, but there is also a hidden reactive power that is always present in the load, that is due to the, for example, the inductance or the capacitance of the distribution network. What is not shown here is probably the load is not directly attached here to this medium voltage grid, but there is a distribution network that generates or absorbs reactive power. And there might be also machines like washing machines and so on that may also have some reactive power. So I put it here. I add this equation. What does this equation mean? Yes?
It's the slack bus?
Exactly. It means that bus 1 is the slack bus. The complex voltage is 1, which means two things. First, it means that the slack bus is controlling the magnitude of the voltage. In fact, that's the main function of a slack bus. It is to control the voltage. And also, it is the angle of the voltage at the slack bus is taken as a reference. So this is magnitude 1 and angle 0. That's what it means here. That's the complex system. As you know, an AC grid needs one slack bus. Sometimes there are complicated systems with more than one slack bus, but in practice, an AC grid needs one slack bus here that dictates the voltage, sets it to a fixed value, and also has another function. By dictating the voltage, it has a side effect, which is the probably most desirable function. Which one is it? Well, it absorbs any difference in power. It balances the power in the grid. So if I do this in this grid, I will set up G2, G3, and L1, L2, L3 will also do what they think they do, but in reality, there will be small differences between the values that I think that I'm using in the planning and the instantaneous value that changes all the time at high frequency. So for example, if I turn on the boiler in my lab here, I increase the power consumed by the grid of EPFL by a minuscule amount. Of course, nobody knows exactly when I will turn on the boiler. So there are fluctuations due to randomness that, of course, we don't want to forecast exactly. Those microscopic fluctuations are balanced by a number of things, but in particular by the slack bus. It's the job of the slack bus to inject more or less than planned in real time. So that is what this thing will do here. Then I have the constraints on the generation of the three buses in active and reactive power. I have the constraints on voltage. This is the constraint on the branch power flow, and this is the constraint on the current power flow here. Usually we don't have both. I'm putting here both in case we need them. The thing that normally makes sense is the constraint on the current, because the physical thing that happens on the line is the current. Is the current that makes the line to heat up, and when the line gets too hot, if it's an aerial line, it will get longer. And when it gets longer, it might touch trees. So one of the problems is that. So we should not get it too hot. And second, the insulators also will get hot and might get damaged here. So as you can imagine, any system has a thermal capacity that cannot be exceeded. This is captured by this formula here. Sometimes this is more or less equivalent to that because the voltage magnitude in normal operation is close to 1. So imposing this or imposing that is often equivalent. So sometimes we take one or the other. Imposing a voltage, a maximum power flow is sometimes used if we have some equipment like transformers that are sensitive to maximal power here. So that's the problem I have to solve. It's a small problem for this example because I have only 3 nodes, so I have 10, 15 variables. So if I have a small problem, I can solve it by brute force. I ask MATLAB with fmin search to solve it, and this is what I did here, and it could be solved. And here's the solution. The solution is given in blue and red. So in red, we have the state equations at the buses. We see, of course, the bus 1 is the slack bus. We see the state of voltage at bus 2, and we see the power injection. So we see that bus 2 is injected 235 megawatt plus some quantity of reactive power. Bus 1 is injecting 400, so it's at maximum capacity. And bus 3 is injecting a small thing, 80 megawatt here. We see also the power line flows. We see here 199 megawatts, so close to capacity of 200 megawatt here. So if we take the module of that, we probably find 200 megawatt on this line, and 300 megawatts, line 1, 3, sorry. Else. No, it's 300 megawatt for this and 200 for those here. So we see that active power flows from bus 1 to bus 2, and from bus 1 to bus 3, and from bus 2 to bus 3 here. That's what the solution of this optimal system will, of this optimization problem will give us. Let's observe a few things here. We see that the maximum loading is done on the bus, which is not the cheapest one. If we had no grid, we would do this one, and this is not the case. And the reason is the capacity constraints here. Another thing that we observe is that we cannot control the power flows like we would do in a road network or in a communication network. In a communication network, I have packets that flow. I can set up routing tables that say those flows will go here and will go there. In an electrical network, we cannot do that because there's the laws of physics, the laws of the grid, Ohm's law, will decide where the power flows. For example, here we see that G1 generates a lot, node 3 consumes a lot. So if I would do I don't see why I need to have power go from 1 to 2 and from 2 to 3, given that the line 2-3 anyhow is saturated here. But that's the law of how electric power flows. We will see an approximation of those laws, which we have seen already 2 weeks ago, the DC approximation, that will help us understand it even better. But as a first approximation, we can think of it as water, assuming those are the G1, G2, G3 are points where you put water into pipes, and the water will flow according to the control variable that you can decide is how high, at which altitude you put the source of water here. We see here that the altitude is given, we can interpret as theta. G1 is at a higher level than G2, which is a higher level than G3, which means power will flow from G1 to G2 and to G3, and from G2 to G3. This is as a first approximation how it is, and it's captured exactly by the DC approximation. Now I redid the same example, but I multiplied by 10 the line capacities here. The branch flow constraints are multiplied by 10 here. Then we see that the result is different. As expected, by doing that in practice, it is as if I had removed the grid capacity constraints. There will still be grid losses, but there will be no capacity constraint. And since there is no grid capacity constraint, we use the cheapest generator at maximum capacity. So G2 will run at 400 megawatt here. And we see here an inversion of power. Now power flows from G2 to G1 and G3 because there's a minus sign here. So the blue arrow means the arrow of reference with respect to which the signs have a meaning here. And we see that this is reflected also in the voltage magnitude and in the voltage angles. The voltage at G2 now is more than 1. So then the voltage at 3 is less than 1 in magnitude, and in angle is positive here and is negative there, which is typical. We see that the power flows tend to follow certainly the voltage angles and also very often the voltage magnitudes. So we see that by controlling the power flow, we are forced to accept the values of the voltage here. So they come as, it's impossible to have voltage equal to 1 everywhere. If we would have this, there would be no power flow anywhere. So we must have voltage differences for power to flow, but the voltage differences mean also potential voltage problems and also potential ampacity problems with the level of the currents in the line. That's exactly why we need OPF. This is why controlling electrical grids must be done again and again. It is to make sure that all those flows occur such that the voltages and the line currents are within acceptable values. And I mentioned the fact that if I add a lot of solar panels, which means if I generate a lot here, like we're doing here, because now we're generating 400, that provokes an increase in the voltage here of this bus. I've shown a very simple case where what we need is to decide what is the value that each generator will produce. Even this simple case, as we will see, provokes a problem, causes an optimization problem that is not so easy to solve. But in practice, we, in addition, have additional constraints and control variables that are typically leading to what is called a dispatch plan. So a dispatch plan is when I have to decide not one value of the power, but a plan. For example, every hour, 1 day ahead, what will be the values here? And in that case, that gives a problem of this kind. There's not much change, apart from, of course, there will be much more variables. So we will lead to optimization problems that will tend to be large in number of variables. That's one of the consequences of what I'm saying here. Also, typically, you may have what is called ramping constraints. It might not be easy or possible to change the power of a generator easily over time. So if for example, a nuclear generator is producing at full power, it is expensive to reduce the power or to shut it down. You cannot shut it down for 1 hour and restart it for the following hour. Some systems do modulation of the power of nuclear generator, but what they do is essentially to release heat into the air and not generating power, but the primary power generated by the nuclear generator is not easy to modulate here. So all generators have constraints on what is called ramping constraints. Gas turbine is the same. If you start a gas turbine, there is a cost. And if you want to change its operating region, then there might be constraints on how fast you can do it. Voilà, here's a small question on the examples we've seen before about power and power balance. Let's see what is true. Is it open? No. Voilà, you should see on this room number, on Speak Up, you should see the poll. Do you see the poll open? I don't, so I restart Speak Up. I close the poll in a few seconds. Closing. And the majority says B, which is the correct answer. So the power that leaves node 1 here is not the power that exits node 2 here. The difference is the power loss. So the OPF solver will give us the value here, and the sum of the two, if we're using algebraic numbers, so we see the power that enters and the power that leaves, and the sum of the two is exactly the loss. So we see that on this line, there is 8 megawatts of active power loss. The reactive power loss does not mean anything from a monetary viewpoint. It's just because the reactive power is no transfer of energy. So this is not important from a monetary viewpoint. It may have some importance because reactive power transportation requires a current, and a higher current will generate more losses due to the active power loss here. So we see this power loss, and that's, of course, what the grid means. So good grids have losses that are a few percent. So a few percent is both small and large. It is small enough so that if we want to control the grid on, I would say, a planning horizon, we can ignore them and add them after. But when we control a grid for example, voltage control or other things, then 5 to 10% are values that we have to care about here. The second question was, is the power balance at a node? So we're asking the sum of active branch powers on node, exiting node 1 on this and that line, and is equal to what is injected by the systems connected to the bus. And that is true, of course, that's the definition of a bus. So a bus is by definition a system that has zero impedance. The impedances are modeled by lines here. So whatever comes in on a bus is equal to what comes out. So there's exact power balance. Yes?
Shouldn't you also say explicitly that it accounts for the power losses?
Say that again?
The slack loss is the power balance is considered like the power flows in the lines, but also the power loss. No.
Yes, of course. Yeah.
But then you should say explicitly no, because you only said it's the sum of the active powers flowing through lines 1, 2, and 1, 3. But you should also say.
So you mean sentence A?
No, sentence B.
Sentence B.
You just mentioned the power.
No, that's exactly true. So the active power, the loss is on the line here, is not here. So the active power that goes here and there is equal to the active power that's injected by G1 minus the active power that's consumed by L1.
And then you don't account for the losses afterwards.
No, but the losses are in the active power. G1 is injected more on this line than one is received at the other end.
Isn't the slack loss designed to take into account also power losses that we'll have afterwards?
Yes, but that's a different story. I mean, this equation is true. By definition, the blue power here is the power that we observe exiting the line, entering the line. So it's the power that includes the losses. A part of this power, it will be lost somewhere. Okay? And it is true that, so the power balance at this node, of course, there is another power balance at that node and at this node. And between the nodes, there are losses on the lines here. And what you said is perfect, is a very good observation. The slack bus function is to balance the system exactly. So if the G2 and G3 inject some amount here, then G1 must be sure that the total, the complete system is totally balanced here. Now, whether the losses are captured by G1 are balanced by G1, G2, or G3 is not obvious in this case here. Here I've done a global optimization problem. I need some amount of power. G2, G3, and G1 have provided this power. Who generated the power that's consumed by the losses is not so easy to say. This is the so-called attribution problem. In a system like this, we might want to say L1 is consuming 100 megawatt. So they will need to pay for 100 megawatt. L2 will pay also for 100, L3 will pay for 500, but who will pay for the losses? The total consumption of the system is larger than 700 because it's 700 plus the losses. Who will pay for the losses? That's the problem of attribution of the losses. It's a very difficult one. It's done only approximately. Since the losses are small, that is okay, but there is no non-ambiguous, there is no universal way of saying who caused which loss here. The losses are the result of the global system operation. So they have to be paid by everyone, typically proportional to what they use here, or using other mechanisms that would require more discussion. Voilà, so far we have seen the theory, and we could stop here. And perhaps in 20 years, the story will stop here when there are good techniques for solving this problem. But this is not the case today. So the problem is that solving this OPF problem, as I described it, is in general too complicated and cannot be done exactly, at least at a reasonable cost. Large operators like the French RTE, which is the systems operator of France, that has to balance the entire French network. They have a research team that has been working for 50 years and several tens of people that work full-time every year on solving this problem. Because this is a non-convex problem, which has a huge number of variables, and this requires a lot of heuristics. So what we will see is what we can still do in an easy way, and what is typically done when we have to do, when we still need to use it embedded in other problems. Why is it a difficult problem? Well, because it's a non-convex problem. So OPF is an optimization problem, and as you know, there are two types of optimization problems. The convex optimization problems, for most of them, there is a good chance that even if they are very large size, there will be good solvers that are able to solve them. And then the non-convex optimization problem, which so far today are, in most cases, very hard to solve, with a few exceptions. There are cases where we can do and say something, but they are hard to solve, at least exactly here. So that's the boundary between the two. The convex optimization problem is typically a continuous problem. Continuous means the variables are continuous. Sometimes in grid operation, we have binary variables. For example, do I decide to start this generator or not? So this decision that I can take introduces binary variable. Binary variables, as you know, they just make optimization problem even worse here. If there's a few binary variables, there are efficient solvers to take care of that. If there's more than a few, it's probably a very hard problem, and this is why the RTE team of people are working on a lot of heuristics to solve them well. So let's say a few words about convexity and optimization problem and how we handle this here. This is, of course, not the main purpose of this work, but given the importance of all those topics in OPF, it's a good revision. You've probably seen that in other courses, but you will probably see that it's still useful. So a convex problem is defined in different ways. It can be defined in this or that way. I will use this one. It consists in minimizing a function which is convex over a set which is convex. So what is a convex function? Well, this is an example of a convex function, function of one variable. It means that the graph of the function is below the chords that we can draw here. That's the definition of a convex function. And a convex set is something where if I draw a line between 2 points, I remain in the set. That's convex. That is not convex here. You can take the dual of this. If you minimize a convex or if you maximize minus f0, a minus a convex is a concave function. So if you maximize a concave function over a convex set, you also have a convex optimization problem. Non-convex functions are functions like this, for example, here. A convex function has has only one minimum, or any local minimum of a convex function is a global minimum. And it's not true for non-convex and non-convex function here. Here you have two local minimum. Here there is a local minimum here, which is the global one. This is what makes convexity so easy, because it's relatively easy by number of heuristics to doing gradient descent, for example, to go towards a local minimum. You move until in the direction of the gradient. By doing that, you will reach a local minimum. And if the function is convex, a local minimum is a global minimum. So that's the good news here. Convexity is hard to prove in general, but there are a number of tricks. For example, if a function is differentiable twice, then knowing whether it's convex is equivalent to looking at the second derivative, the matrix of all second derivative, and seeing whether the matrix of those gives what is called a positive semi-definite quadratic form. And so that's, I would say, the most of the time, this is how we test whether a function is convex. And then you have combinations. For example, if you take a linear combination with positive coefficients of convex functions, it remains convex. Max is convex, and a number of things that I will not go in detail. So this I've mentioned already here. So let's test your understanding of convexity on this simple example. Here are three optimization problems. The first and second one are in one variable. The second one is in two variables. Which of them, if any, are convex problems? I close in a few seconds. Majority says F, which is the correct answer here. Of course, A is not convex because it's the maximization of a convex function. X squared is the prototype of a convex function. It's an example to keep in mind. This is convex. X squared is a convex function, and the domain of definition here is convex, is an interval. C is convex also because the optimization function is linear. So linear is both concave and convex. So since we max, it's concave here. And the set of constraints, which are all given by linear inequalities, is also a convex set. Because a linear inequality gives a half plane, which is a convex set. Now, the intersection of convex set is convex. So that's a convex set over maximization of a concave function over a convex set. So that is a convex problem. Not in the standard form, but it's a convex problem. Is this one a convex problem? I close in a second. Majority says C. Majority is always right today. It's wonderful. Well, the constraints defines a convex set because this is the disk, the inside of a circle, so it's convex. Now the objective function, well, it depends. If A and B are positive, yes, it's a convex function. But if they are not positive, it depends. For example, if B is negative and A is, for example, this one, x squared minus y squared, this is not convex. And to get this, we can compute the matrix of second derivatives, which gives this. Now, it's not positive semi-definite. Positive semi-definite means if I take if I consider this as the matrix of a quadratic form, so if I consider xy times this times xy, so that gives a x squared plus b y squared, is this always positive? That's the definition of positive semi-definite. Then yes, so is this always positive? No, it depends. There are values of x and y that will make this negative, and values of x and y that will make it positive. So this is not positive semi-definite. That's a bad problem. This one is not a convex problem. That's the kind of problems we have in the OPF, exactly. We exactly have this type of problems. So is this problem a convex problem? Closing in a few seconds. Dirac on B, the answer is no, that's the correct answer. Here the set is a circle. That's not the disk. The disk is the circle plus the interior. The circle is just the boundary, and the circle is not convex. If I draw 2 points on the circle, all the points in between are not in the circle. They're in the disk, but not on the circle. So this is not a convex set of constraints. It's not a convex problem. So this is a non-convex problem, but is it possible to transform it into a non-convex problem? Into a convex problem, thank you. It's non-convex for two reasons. I mean, the objective function is not convex, not concave, and the set of constraints is not convex. So it looks very bad. Closing the poll. The majority says A, but I could challenge you, yes, but how? So that's the correct answer. Yes, it is possible. But it's not so easy to see why, other than having the solution. Well, we can see that the constraints here, it's an easy problem because it's in 2 dimensions with a constraint on the disk. We can parameterize the circle, and we see that y must be equal to plus or minus square root of c squared minus x squared, and x must be less than between minus c and plus c. So that's a constraint on x. So this is equivalent to this minimization. Now if I number crunch that, this is 2x squared minus c2. So this problem, if I reparameterize, I transform the problem, I obtain another one which is equivalent. I have a solution of this one, I know how to solve that one, and vice versa. But here we see it's a minimization of x squared over a set which is an interval. That's the number x that are between minus absolute value of c and plus absolute value of c. So this is a convex problem here. Well, that's the take-home message for now. Of course, in this course, we will not work on techniques for solving optimization problem. That's the job of another type of courses, and we will use packages for that. But the problems we will have always is to pose the problem well, and once the problem is well posed, possibly to transform it in a way such that it becomes solvable by the packages that we have. In particular, we have to make it convex here. So transforming a problem is something that we will need to care about. This is why we're doing all these drills on optimization. Voila, I think it's time to do a little break. So it's 10 o'clock. We restart at 10:15. So we are ready to restart. Thank you. Linear programs are, of course, standard convex problems. They are the ones for which we're able to find efficient solutions, even if they are very large. So not surprisingly, we will try very often to approximate our problems or transform it into a linear program. Linear program is typically a linear objective function subject to constraints that are put in this form here. Min or max doesn't change because this is both convex and concave here. Here's an illustration of the problem we saw in the previous quiz. We see that the constraints are convex simply because they are intersection of hyperplanes. And one property of a linear program is that the optimum is always at an extremal point here. So the various solution methods, we're trying to find those points here. Here are two problems that are not formulated as linear programs, but can they, by transformation, can we obtain linear programs by transforming them? That's the question. Closing the poll. The majority says B, which is the correct answer. Indeed, the problem A, which is quadratic, doesn't seem to be easy to transform it. But here, let's discuss this one can be transformed. Let's discuss how it will be transformed into some linear program. This is B. This is my problem I have. The non-linearity comes from this max function here. Right. Now there's a trick, which is this one. I introduce a dummy variable, t. I add constraints on this dummy variable. T is larger than x plus y, t is larger than 2y, and I minimize t. So t is the max, if you want, is f0. I replace f0 by a variable, I minimize the variable, and I add those constraints here. And it turns out, now this is a different formulation. B prime is not exactly the same problem as B, but they're equivalent in the sense that if I solve B prime, I have the solution of B. And why is it? Well, because the key observation is if I say that a number t is larger than two expressions, it is equivalent to saying that this number is equivalent to the max of those two expressions. So this is equivalent to saying t is larger than the max. Now I minimize t. Well, the only constraint on t is that t is larger than the max of those functions of the other variables. What is the solution to that? What is the smallest value that is larger than the max? Well, it is the max. So I add a constraint here. I say, I add the constraint that t is larger than the max here, and I ask, what is the minimum value of t? Well, the minimum value of t is precisely the minimum of this function here. So those two elements, first, adding a variable, adding a constraint on the variable which is an inequality and minimizing it is equivalent to finding the minimum of the function. And second, several inequalities can replace a max here. We can do this in general. It's called a max removal transformation. That's a trick that's very often used, in particular if we're interested in keeping optimization problems that will be linear, which is of great interest because if our problem is linear, it will be considerably easier to solve. So we'll be able to solve problems of much larger size than if it's not linear. Then in general, if I have a problem of the kind, an optimization problem that can be written in this form, x is a optimization variable that may be very complex, perhaps many, many dimensions, and the objective function is a sum of sub-objective here, then I can add intermediate variables here. Problem of the form. I have to solve a problem, an optimization problem, where the objective function is a combination of max of functions here. So in our example, we had only one. So f1 is the max of a number of g's here. Then this is equivalent to adding for every max term here, a dummy variable here, and adding this constraint here. In particular, if the gi, gj are linear, this will automatically give us a linear problem here. So take-home message, if I have max in the objective function, I can get rid of it and the problem will still be linear. For example, here is a slightly different a variant of what I said. I have to minimize a function here, which is absolute value of x minus y minus 5. And somebody claims to me that this is the same as a. Somebody claims that I can. This is not a linear problem because the absolute value is a, depending on your viewpoint, you can consider it as a nasty function because it's non-derivable. It doesn't have a derivative at 0. It's a singular point in 0. Or you can consider it as something simple because it's equivalent to a. At least somebody says to me it's equivalent to a, or someone else claims it's equivalent to b. Is any of those two guys right here? closing in a few seconds. Majority says A, which is the correct answer. The observation is this one. Absolute value of a number is the max between this number and the opposite of this number. Doesn't seem very useful, but that's a trick that can transform something as a max of linear function. So absolute value of this expression is the max of those two terms here. Therefore, I can say this is I can apply the max removal transformation that says my objective function is the max of two terms. For each of the terms, I introduce a constraint. I introduce one dummy variable for each function, which is a max. So here, one, t. And for each of the term, I introduce the constraint t is larger than each of the terms here, which are the two opposites. Of course, b is wrong because the inequality is in the wrong size. The mean of t here, what will be the mean of this problem? Minus infinity, exactly. So it's an unbounded problem. T can be as negative as you want and satisfy the constraint here. So B is not a good formulation here. Voila. So why did we spend half an hour playing with problems? Well, because problem transformation is really one of the key things we will need to do, because we don't have a global package solution that can solve our problem. We will need to work on the problem here, and we will see many instances in the rest of the scores here. Now back to the OPF problem. The AC OPF problem, which is the original problem we have said, is unfortunately non-convex here. And the reason is that the constraint, the set of constraints is non-convex. Let me illustrate numerically with one example. So this is a very simple, the simplest grid. I have two buses, a slack bus and bus 2, and I assume that at bus 2, the only constraints I have are the voltage magnitude at node 2, and I ask the question, what are the feasible power injection, PQ values of injections at node 2, such that the voltage magnitude at node 2 is satisfied here. So we can compute it exactly, because that's a simple example. That gives the red area. That's the PQ plane. For some reasons, the electricians put the first dimension in the y-axis. It's a weird thing, but that's invariably how they do it. So P is on the y-axis, Q on the x-axis. And we see that those are the feasible, the red area is the set of feasible values of PQs at this node, such that the voltage here will be in magnitude less than 1. Of course, this is not easy to interpret exactly, because those are complex impedance, so everything is two-dimensional. And in practice, very often we don't work, so this is, as you see, a non-convex area. For example, if I have a feasible point here and a feasible point there, the line that goes between the two is not feasible. It's a bit an extreme case in the sense that if we operate in this region here, we are in a region which is at what is called the limit of feasibility. If I increase, for example, see if I have a P which is close to -4, that means I'm consuming 4 per unit of power here. If I want to increase how much I consume, I have to inject a lot of reactive power. I have to go in this direction here. Very often we work in a region that's closer to 0. So closer to 0, it looks very much like a rectangle. So in practice, very often this will not be a problem, but we are never sure in which region we're truly operating. In particular, when we are close to the capacity limit of the grid, we can come to such point here. So that's really the problem. That's the ACOPF problem. You can imagine this is a simple case, single phase line, a single node, set to only 2 variables. If you take a larger grid that has a few tens or hundreds of nodes, of course, the number of dimensions will be a few hundreds, and this will, of course, not be as simple to illustrate here. This is why people have worked on practical problems. We will see 2. Of course, there is always the brute force approach, which consists of trying to solve the non-convex problem by using non-convex solver heuristics. But it's also important to know 2 very frequently used methods. One, the DC approximation that you've seen already 2 weeks ago. We will see it again in the context of optimization. And sequential linear programming, which is a very complex name, so it's something very simple. It simply means we linearize the problem using the first order Taylor series expansion here. So those are the two very simple methods. You've seen for load flow, you've seen a number of other linearization or approximations, and there's a vast literature about this that we'll discuss at the end. But those are really the two methods that are extremely frequently used and that can get you a long way. The DC approximation that we'll see now is very simple. It is too simple. It ignores the power losses, so of course it cannot be used to solving everything. But if the losses are not very large, it gives some very simple approximation that allows us also to reason about the grid. The DC approximation is the approximation that is used for solving the market and allocation problems, for example. Sequential linear programming is the simplest, more exact method that is not too complicated to use. So back to DC approximation. The DC approximation is done when we can assume, so here is a line model, an electrical line between two buses. A line model is typically, if you take it in its most general form, for single-phase system. If the system is balanced, we know that we can take a single-phase equivalent. If it's not balanced, we will have a more complex things with all the phases represented here. In this module, I will speak only of single-phase systems. So a line model is typically a longitudinal impedance and transverse impedances here, which are, of course, there's no physical connection between the line and the ground, otherwise it will. But there are inductances or capacitance, depending on the type of lines, that may generate some reactive power to circulate between the line and the ground. So that's the generic model of a line. And we're interested in the longitudinal component. The impedance has a resistance and a next component, a reactance. Reactance, correct? I'm checking the vocabulary because it's a bit cumbersome. And what we're mostly interested in is the inverse of that, which is called the admittance. So the admittance is 1 over the complex impedance, which gives those values. The real part of the admittance is given by this formula, and the imaginary part given by that. For most aerial lines, the imaginary part is negative. So the x here is positive, and the b will be negative. The DC approximation is when the r is small compared to the x here, or which is equivalent when the g is small compared to the b, which is typically the case for medium voltage to high voltage lines in AC systems, where the resistance, the induction, and the capacitance effects are larger than the resistance effects here. And as we know, when that happens, most of the time it means the voltage magnitudes will be close to 1, and the voltage angles are small, and we can do the using these approximations. If I write the power law equation at a bus, or on a line here, on line KL, this is the power law equation that comes from this here. This is the line current, is the longitudinal component. There's also a line current that flows into the ground, which is captured by this element. That's the exact complex number representation of Ohm's law on this line here. I'm interested in the active power. As you know, the active power is the real part of the complex power. So I take the real part of this, and I obtain this formula here. Now, if I assume that the voltage magnitude is 1 and the voltage angle is small, the voltage angle is small means I will assume that the complex exponential is equal to its first order element of its Taylor series expansion, which is given by this formula here. If I number crunch all of this together, I obtain this formula, which is the DC approximation that says that the power, the active power that flows on line KL between bus K and the bus L is proportional to the angle difference, theta K minus theta L, or the angle of the voltage here, multiplied by minus the imaginary part of the longitudinal admittance, which is approximately 1 over the x part, 1 over the reactance here. So this is the DC approximation on the line. So capital B here is a positive number here, because B is typically a negative number here. We can put that as in the form that you've seen for the load flow. If I call Pk the injected power at a node, that means the sum of all the powers that is injected into the node minus the powers that flows out into the lines, or the power that comes from the lines, we obtain this equation here, and which in matrix form, this is what you've seen 2 weeks ago, can be put in this form. P is a matrix B times theta, where the B element is minus the what I call the capital B here, which is a negative term, and the diagonal term is the sum, due to this term here, is the sum of the BKL here. It's a degenerate system. It's a linear system of inequalities. We can do a simplified power flow. The power flow problem is to find the theta given the P, but it is degenerate because we know there is this additional constraint. That's always true. The sum of the powers is equal to 0, which is physically not true, but it's true in the DC approximation, because the DC approximation ignores the power losses here. Let's do it for this small example here. Here I'm showing the admittances on the line in per units. So the values are given here. The real parts don't matter. The only thing that matters are the imaginary parts. That gives us those power flows equations. That's the injected power law at line 1, at bus 1. This is the power that flows on line 1, 2. The power that flows on line 1, 3. 22.2 is the imaginary part here, minus the imaginary part of the line impedance, admittance. And the sum of the 3 powers is equal to 0. You can verify that if you sum the 3 equations here, you do obtain 0 equals 0, because the different theta will cancel out. So that's the load flow equations here. Right. Now we can solve the load flow explicitly here, and the branch flows are in fact simpler. They're given by those formulas here. Now if we set 1 as the slack bus, that means theta 1 is equal to 0 here. So having simplified the grid equations makes the OPF, of course, much simpler. The OPF is called the DC OPF in this case. So the DC OPF ignores totally 2 things, the power losses, but also the reactive power. So any constraints that involves reactive power or imaginary parts of currents are not acceptable. So typically we replace the power constraints on the line, which are in apparent power, or more exactly even on current, a complex current. We replace them by constraints on maximum power on the lines here. So we assume we admit only some maximum active power flow on the line, which is only an approximation of the true constraint. The rest, those are the load flow equations we gave, and this is the problem we have here. Now, if the cost here is linear, that's a linear problem. At least the constraints are all linear here, and therefore it makes a problem trivially convex. And we're able, for example, to solve this dispatch plan for this thing here. When I solve it, here is what I obtain. I obtain this formula here. There's only active power. The directions of power are given here. And we see the DC approximation helps us understand also the physics of AC grids. We see that the power flows exactly proportional to the angle difference. So since power in the optimal is flowing here and there, we see that the angle here must be less than 1 and the less than 2 than the angle at 2 here, which is truly what happens here. We see also a value which is called the marginal cost, that I will mention in a second. Those are the costs that we have if I want to increase the demand at this node. We see that because of the line capacities, the restriction here is 200 megawatt. That's a binding constraint for this problem here. G2 is not running at full capacity, but G1 is running at full capacity, and the power has to go partly via node 2 in order to reach node 3, even though the capacity of the line 1, 3 is not fully used here. So this power could flow here, but that's not the way the laws of powers are. In order for power to flow, we need to set the values of the angles. Once the values of the angles are set, because θ1 is larger than θ2, there will be some power that will flow from 1 to 2, even if we don't want it. It would make more sense if this would be routers or switches and not electric buses. We would send all traffic here, but this is not how it flows in electrical grids. I did again the same thing with let's look also at the marginal flow and the marginal costs. We see here the definition of the marginal cost is the additional cost I will need to pay if I increase the demand by 1 unit here. So we see that at node 2 it is 1 franc, at node 1 it is larger, and at node 3 it is much larger here. Why is it so? Well, because of the different constraints that we have on the grid. If I want to have more power here, I will need to generate it partly from G3. So the cost will be, the additional power will be generated from G3. Whereas if I have more power consumed here, I can produce it locally. This is used in electricity markets Europe-wide, where because the grid, and this is a simplification of the European grid, but this is how things are. The grid is not large enough to allow all power flows to flow in all directions at all times. So we need to do optimal power flows to decide how much will be generated here and there. And as a result of that, the prices are very different. They are called the locational marginal prices. So the price of electricity in this region is much less than in that region. And the cause is that in order to obtain more here, the grid is not able to transport more. You have to generate it locally, which is at high cost. If I make the grid more powerful, I multiply the capacities by 10, the problem goes away. We will see that the marginal prices will become 15 franc here when it was to 25 here. Why is it? Because now G2 is saturated, but in order to generate more, if there is more demand here, it will have to come from node 1, which is at a cost of 15 here. So having a more powerful grid in this case had a dramatic effect on the locational marginal price and on the price of electricity at this part of the grid here. That's exactly the challenge for the European grid in the coming years. There is more and more variability. The power profiles are changing because we are changing the generators. The generators are solar panels, which are distributed everywhere in Europe, or will be more and more distributed everywhere in Europe. There's also wind energy that comes more and more from the North Sea, which is the major source of wind energy. That works when there is wind. When there is no wind, then there might be more solar coming from Spain, for example. So the flows are constantly moving and changing. And the grid, the European grid, is not what we call a copper plate. Copper plate is the expression that is used to mean it's completely transparent. You can do as if there would be no constraint, but there are constraints, and they are visible in those prices here. We can also compare, if you compare to the true ACOPF here, so those are the values we see here. We see that the optimal value are 233 and 400. If I compare to the true ACOPF, you will see a difference, but you will see that the difference is small. Oops. So you see 235 into the 233 and here 400. So the differences are small. Of course, what is not captured in the DCOPF are the losses and some other constraints of the grid here. So I have obtained a linear problem. I can make it a little more complex if I add what I call the unit commitment issue. Unit commitment, I've mentioned already, is the decision whether we use a unit or not, which comes associated typically with a startup cost or a shutdown cost here. So here I'm saying I have a number of units to to control. I do it over several slots of time, here over 24 hours, 1 per hour, 24 times. So I have a cost associated. Then I need to decide whether I start a unit or not. If I start it, that is, if W is equal to 1 here, so this quantity will be 1. If it was down in the previous time and is up now, I will pay a startup cost. And similarly, if I shut down, I will pay a shutdown cost here. And that depends on binary variables, the WI, which are 0 or 1 here. So by doing this, I have a problem which is now no longer linear, not convex. It's called a mixed discrete continuous optimization problem. And it can be solved if the rest of the constraints are linear, sometimes quadratic even, and if the number of binary variables is not too large. There are good heuristics based on branch and bound that most of the time will work well and have the goods property that they will always converge to some solution, which might not be the optimal, but at least is always feasible. So that is the state of the art, and that is very often used, and you will have to use some of this in the lab here. Little quiz on the DC approximation. I close in a second. Closing. That was an easy one. The answer A and B are true. That's the essence of the DC approximation. And C, of course, is not true because the essence of the DC approximation results in the observation, that is the angles, the voltage angle that dictate at first order the power flows. So they are the key variables here. No, that's not the correct. I reopen it with the up over here. Well. So you have to reuse the same pole as the first one and give, but the question is different now. With the DC approximation, the question is on power flows here. I'm closing in a few seconds. And the correct answer is D, which is again the majority vote. Branch power flows are of equal magnitude in both directions, and there is no active power loss. Well, the two mean the same thing, in fact, here. So that's the property of the DC approximation. And the problem of the DC approximation, it's the main problem of the DC approximation, it doesn't compute the losses. So it's used by markets because it allows you to have a very big optimization problem with binary variables and decide which generator should do how much, but it's not the end of the story because it ignores the losses, and the losses need to be paid by someone at the end of the day. They are generated, so they need to take care of this. And it is called this way because it models a DC grid power flow. This is wrong. It models something else. There is an analogy to a DC circuit, but not with the. But we need to change that, not for the power flows. The analogy is from which we replace power by the current in a DC grid. So the current in a DC grid follows the same equations as the DC approximation for the powers in an AC grid, where the voltage are replaced, the numerical voltage in a DC circuit, the voltage is a real number and has no angle. It replaces by the angle here. So DC approximation, of course, is not sufficient, even though it's used a lot because it can be solved, can be used as a first step in an allocation. Then we need to, for example, to compute what better allocation that accounts for the losses here. And the simplest solution, which is very efficient, is always used, is called sequential linear programming. The idea is to linearize the problem around some operating point. So we start from an initial guess, for example, obtained from the DC approximation, and then we replace the non-convex problem by a linearization of the problem here. So remember that we can write the power flow equation in a very compact and compressed form. In this form, there is a mapping that I call F from the complex voltage to the complex power injections at all buses, and I put separately the slack bus here. Right? So the slack bus here is 0 here, and V is the vector of all complex voltages, and except the complex voltage at the slack bus, because this one is equal to 1. So I have a grid with a slack bus 0 and other buses, and load flow problem is, if I give you all the S, find the V. That's what you know how to solve with a Newton-Raphson. Now, if I know a solution, a load flow solution, for example, what is typically done, I solve for the optimal S or the optimal P using DC approximation. That gives me an S with a reactive power equal to 0 and active power given by the DC approximation. I do a load flow, and that gives me a solution V hat and S hat, which is not the true solution, but is a feasible solution of the grid that was derived from the optimal value of the DC approximation here. Now I can linearize those equations by replacing the function by its linear approximation given by its derivative or its differential. So this nabla F means the Jacobian matrix. That's the matrix of all differentials of F. Remember, F is a mapping that has multiple coordinates. F1 is the power S1 as a function of V. F2 is the power S2 as a function of all the V. So it has multiple coordinates. It's a vector, and the argument is itself a vector. So the Jacobian is a matrix, n by n matrix, with all the possible combinations of partial derivatives. If I wrap the Taylor series expansion, I have many orders. If I take only the order 1, I have this linear approximation here. So this linearization is accurate locally. It's true exactly for S hat, V hat, of course, trivially. And in practice, the derivative is not, the variability is not very large. If we're operating in a region that's far from the limit of feasibility, in practice, this is often a very good approximation. So if we are not operating, for example, if we're operating here, that might be a bad approximation, or it might be true only a very small example. If you're operating in this region, that may be a very good approximation. So still, so that's the essential idea, but there's a few details to fix because sometimes the devil's in the detail. As you know from the load flow issue, there's always the decision, do you take rectangular or polar coordinates? There's no good solution. For some problems, one is better, from the other is better. So very often we take the rectangular coordinate for the power because there is a physical meaning to the real and imaginary part of power. The real part is the active power, the power that truly is useful, and the reactive part is the reactive power, which has zero mean. So there's a physical meaning of active and reactive parts. So very often that's what we use. Very often we use also polar coordinates for the voltage, for the state of the grid, because that's the real part of the complex voltage has no universal meaning. It depends on where the angle, what the reference angle is taken. If I decide that the reference is 0 at this node, then the imaginary part is by definition always 0. So the real and imaginary part of complex voltage have only a meaning that depends on the convention. Where do you decide that the 0, which angle do you take as reference? So they don't have a physical meaning per se, unless you give the physical reference, unlike for power. So very often for that, but the voltage magnitude has a physical meaning. You can measure it with regardless of time reference here. The phases, of course, have a reference only with respect to a reference, but as we know, they also have a very important meaning in the sense that the phase differences will tell us a lot about the power flows here. So very often, that's what we take. So if we write in this form, of course, this form here is a more complicated form than the one I wrote before. There's lots of cosine and sine. It's an ugly formula with trigonometric functions. And if I write this is what I obtain. I need to take the Jacobian with the matrix of all derivative here. And this is sometimes called the load flow Jacobian matrix here. If we are interested in active power, then we obtain only this. Okay, that's standard here. Let's see an example where we can use this for one of the control problems I mentioned in the introduction of this lecture. That's the problem of controlling the overvoltage due to PVs here. And the solution, well, there are multiple solutions. The solution that's deployed, for example, in Switzerland by some operators like Group A, what they do, they simply curtail the excess production, which means you invested into putting a PV roof on your house, but on a sunny day in June, everybody is generating too much, so they will shut down your house, perhaps, or not, or your neighbor's house, so they will reduce the power generated by your PV. That's a brute force approach. It's very primitive. Some operators in Switzerland, they say, of course, they pay to you, they estimate how much they've curtailed, and you're paid for the generation that you have not generated, because the operator finds it less expensive to pay you for the power that you have not generated than to pay for another solution that would not dump any power. The other solution would be, for example, to put a battery somewhere in their grid and absorb into this battery the power here. Many grids do that, but if you have just a few nodes that generate over voltage, and that happens only a few days in the year, then you pay a few thousand francs a year to those customers for the power they have not, that has been curtailed. It's cheaper than to maintain a battery. So let's assume we do this here. We curtail the power here, and we want to control the voltage here, all the voltages, with all the constraints of the grid here. So we can do a DC approximation, but the DC approximation will not account for the voltage angle, the voltage magnitude, because it sets it to 1, so that doesn't help. So what we can do is we can do a linearization around one operating point, because typically we're measuring the grid. We see where it is now, so we know a load flow solution by state estimation. So I will have to solve this problem. So in this problem, what did I take as objective function? Here I took as objective function two terms. One here, which is a penalty for the voltage deviations from the nominal value. Here everything is in per unit. Little v means the voltage magnitude. I take the sum of the voltage of the distance of all voltages to 1. Ideally, they should be very small. Plus also the price I'm paying for the power that I draw from the slack bus. because in this grid I will pay for this anyhow here. So W is truly the monetary cost, and this is unitless here. If I linearize this, what will I do? Well, I take the same problem here. My variables are all the power injections here. I linearize around the point that I've measured, and what I do is I replace the grid equations by these linearized grid equations, where my J here is my load flow Jacobian matrix that is estimated at this value, P hat, Q hat here. And in addition, since I have the slack bus power, I will need also to linearize the slack bus power. Typically, we need to handle in load flow equations, it's probably familiar with that, we need to handle the slack bus different from the others because the constraints are different here, but essentially it's the same. We linearize everything, and this is what we have obtained here. If I do this, I have power here that are not the truly physical power, but are the approximations of the physical power given by this linearization here. And I add here operational constraints that are, for example, I would like the power P and Q to be less than some quantities of interest here. So that gives one iteration of what is called a linearized voltage control here. If I do this, I can do it like this here. I'm only approximately solving the problem in the sense that the optimization problem I'm solving is not the exact one. And the solution I will obtain does not exactly satisfy the grid equations, which most of the time is good enough for voltage control. Voltage control is not something that you want to be accurate at the percent. If your voltage is within 10%, it's okay. If it's within 10.0001%, it is still okay. So a small error in the is okay. But if we do not want to do such errors, we can do an iteration, which consists in linearizing repeatedly. When I solve the optimization problem, where the grid equations have been replaced by linearization, I obtain some optimal value. This optimal value does not satisfy exactly the grid equation because it satisfies the approximate grid equation. What I can do is I can do a load flow or replace the values by a value that satisfies the grid equation exactly and obtain in this way a second operating point. That's what we do exactly here. So I need to minimize some function of the grid here. I start with some initial value, P0, Q0, those are the power injections, V0, theta 0. So the 0 in superscript means the index of the iteration, not the slack bus here. And those are the grid equations in here, polar coordinate for the grid state here. I compute the load flow Jacobian at the point that I have, so initially at my value here. Also the Jacobian, the gradient for the power at the slack bus here. And I solve this problem. This problem is exactly what we said before. I solve the problem where I have replaced the grid equations by their linearized version, where the linearization depends on the load flow Jacobian J, which depends at the point where I am. When I have solved this, I obtain a point which I call pk. I obtain a new value of the point here. And the point that I have obtained, the values of v and theta that I have obtained, satisfy this exactly, but they do not satisfy the grid equations exactly, the nonlinear grid equations exactly. So what I can do is I can make them solve them exactly. That is not a load flow, because here I'm assuming I take the v and the theta, that is the solution of this optimal thing here. So the solution is v theta, and the PQ component, I call them with a bar here. I will throw them away. They will not be used. I will replace the P bar, Q bar, which are not the exact power. They are satisfying this linearization. I replace them by the true values here. So what I will have here, I will have another point, which is now V, K, theta K, PK, and etc. And I will do it again. I will linearize at this new point and solve the game. What have I obtained when I do this? At every iteration, I have obtained something which is optimal solution of the approximate problem, but thanks to the correction on line 7, is an exact solution of the load flow. It's exact, and the V component has been taken from the solution of the optimal solution of the approximate problem. So I've not changed the V theta, but I have modified the PQ to make them satisfy the load flow solution. If we are lucky, this will converge in the sense that this condition will be true. The difference between two values at two iterations will become small. It does not always converge. Very often it does. In particular, if we are solving a local problem, we're trying to go away from a local solution, it will do. If it does not, then we stop simply after a number of iterations. What we have obtained is something that is satisfying the grid equation exactly and is a solution of the approximate problem. With a little catch here, that's, I call it version 1. This solution, I have obtained it by modifying the P, but not the V. So in my system here, I have constraints on the electrical state, V theta, constraint on the power injections, PQ, and perhaps constraint also on the transformer, if there is one at the slack bus, P0 here. Those constraints are satisfied exactly by this, but not by that, because I've modified the PQ. If I converge, I don't care, because at convergence they're quasi the same, so I don't care. If I stop before convergence, and that happens sometimes, because if we do a system that runs in real time, we want to be sure it converges, so we will impose a number of iterations and stop at a fixed number of iterations. Then it depends. I may not be happy with that. I may be happy with that if my constraints are strict constraints on V and theta, because I know my V theta will satisfy the constraints, so will the P bar Q bar, but the PQ that my system will return are not exactly equal to P bar Q bar. They're a bit different, which is sometimes a problem because I have very often the constraints on P and Q. For example, a generator cannot generate more than 100 megawatts. So I have a constraint on P. My optimal solution says the P bar satisfies the 100, but the P that I compute with the load flow is 101, then I do not satisfy my constraints here. So very often we have strict constraints on power injections and loose constraints on electrical state, because the electrical state, if I say the current on the line should not be more than 30 amps, then there is not a law that says if you're 30.0001, your system will explode. That's not the case. So 30 amp is a constraint that can be violated if you violate by a very small amount here. So satisfying the grid constraints only approximately is most of the time okay, but satisfying the power constraint is not okay, because the power is a physical limitation of a system here. Well, no big deal. The only thing you need to do is you need to invert the correction you do. So we do exactly the same thing here. We iterate. We find a solution which is an exact solution of the approximate problem, but we consider the electrical state to be not the final value we will return. We will correct the electrical state while keeping the PQ. This is called doing a load flow. This is what you've seen with Newton-Raphson and other methods. So you need to do a load flow for that, which is more expensive. It's much more expensive to do a load flow than to simply compute the PQ that corresponds to some V theta. That's the inverse problem here. But that is often done because the constraints are often done on PQ. Voilà, so for example, if we want to do a voltage control formulation with sequential linear programming, here's the algorithm we will have. We start with an approximate solution, for example, for DC OPF, and then we iterate, we minimize this objective function subject to this linear constraints here, and then we correct what we have obtained. In this case, if we care about exactly the V theta. We will not do a load flow, but the direct problem until we iterate here. And this will give us methods of controlling the voltage in my grid and minimizing the power exchange, the power I'm consuming from the slack bus through this method here without having to solve a big non-convex problem here. So if you compare the two, you see that here we have iterations. Here we don't iterate. When do we do this one versus that one? Well, it depends on the frequency for voltage control. It depends how fast you do it. If you do your voltage control once per 15 minutes, perhaps you will do this. If you do your voltage control every minute or every second, then probably you will do that, because by the time you do it, the quantities have changed, so you will measure again another operating point and do it again and again. So it will depend on the frequency of what you're doing there. Some terminology that's often used in the lab or in the other contexts here, what matters is really the J, the load flow Jacobian matrix for linearization here. So it's returned by many packages that will return it for you, and I'm sure you've used it while doing the load flow lab here. The coefficient, the inverse matrix is very often called the voltage sensitivity coefficients, because if I invert this linearization, I can have the expression of the voltage as a function of the power injections. And so you've seen in the load flow solution, this is one way of doing an approximate load flow. And this is also very often used, for example, for doing voltage control. If I know this voltage sensitivity coefficients, well, what we're doing in the voltage control problem I said is to use exactly the voltage sensitivity coefficient here. Voila, so that's for this fairly simple method with only a little catch. With a little catch on how to solve the solutions exactly. So another question here, I don't have it on my thing online. I say what is true. Say what is true. Let me add it here. I close the poll in a second. Closing. And the majority says B, which is the correct answer, of course. If we converge, we satisfy the AC power flow equation exactly. If we don't converge, then we need to correct, and we correct either doing a load flow or a direct computation of the power flows, depending on what constraints are important for us here. And it's not a true minimizer of the ACOPF problem, but it's a true minimizer of an approximate ACOPF problem. And with DCOPF, Closing the poll. Of course, the answer is no to everything. DCOPF has the virtue of being simple, but other than that, it's not exact. So it's not a true minimizer of the ACOPF, and it does not satisfy the AC power flow exactly. In particular, it ignores the losses, which is embarrassing. Last quiz before the break. I'm proposing here two formulations of the voltage control problem, where I ignore the slack bus power exchange. So I assume I have a closed grid, or I don't care about the slack bus because it's my own and I don't pay for it. What can we say? I close the poll in a few seconds. Closing. We have a tie. The answer is A. So first about convexity, well, we have the absolute value, which is a convex function. Absolute value is convex, and even more than that, we see that by adding supplementary variables, we will transform that into a linear problem. So that's no big deal here. Now, those are the linearized state grid equations here. And here the difference, they are linearized in a different way. But this is the same as that, because this is V minus V theta equal A P minus P theta. And A minus 1 is J, or J minus 1 is A. So this equation is the same as that. Modulo numerical errors. When we compute A, which is J minus 1, there might be small differences. But if we ignore the numerical inaccuracies due to the inversion, they are the same. Here. So you do whatever you want. I would do this because I don't need to invert here. So this is a simple formulation, OPF, style, linear. In fact, linear, we can transform it into linear of the voltage control problem. This is how we can control the voltage in an AC grid. Voila, time for a little break. After the break, I'm a bit late, so we resume at 11:30, and we will discuss about the locational marginal prices. So we're ready to restart. And the topic now is the locational marginal price, which per se could be a very simple topic if we are very clear about the terminology and the framework of constraint optimization. But perhaps it's worth spending a few minutes on discussing results on Lagrange multipliers. This is well known, this is used all the time, but my experience as a teacher and as a student also was that on the surface it's very simple, but in details, it looks very complex because I had a course on convex optimization. It uses some formalism. Another course on constraint optimization uses another one. Then another course on linear programming uses yet another one. So the details can be a bit confusing. Fortunately, there is a book by Stephen Boyd and Van den Bergs that removes the confusion by proposing a standard form that encompasses all the forms that exist. So one of the problems of optimization is that the standard form of a problem is not the same for every author. If you look up Wikipedia for Lagrange multiplier, for example, you will find a form of an optimization problem, which is not this one here. So that's part of the problem, but there is a solution. The solution, at least my solution, the one I propose, is to stick to one form, because this is, time has shown that this is an excellent reference. So define an optimization problem in exactly this form. So what is this form? I minimize a function, which is defined over a domain, D, plus with constraints. The constraints are of two types, negative inequality or equality to zero here. So put it always in this form. If your problem is in a different form, if it's a maximization, then you simply change f into minus f, and maximizing minus f is the same as minimizing f, or minimizing minus f is the same as maximizing f. So you can always transform it to obtain this here. If you have no inequality, then it's fine. If you have no equality, then the set is empty, that's all. So that's the most general form. Note that the domain of definition is defined formally differently than the inequalities here. So there are two sets of constraints. There are implicit constraints in D and explicit constraints here. Some standard terminology, I'm sure all of you know it exactly already, but it doesn't hurt to revisit it. The problem is called feasible if this set of constraints is not empty. Right? So if there's always one x in D, that satisfies all these inequalities and equalities here. If the problem is infeasible, the optimal value of the problem by convention is called plus infinity. It has to do with the convention that the infimum of an empty set is plus infinity. If you take the infimum of a set that's very small, then if you reduce the size of the set, the infimum tends to increase because you have more and more constraints, fewer and fewer systems, fewer values make it possible. So that's the convention. So optimal value plus infinity for a minimization problem means the problem is unfeasible. Now, a problem like this does not always have a solution, even if it's feasible. We saw an example an hour ago when we had a minimization. We had T that was satisfying inequality constraints such that we could have T as negative as we wanted. So the optimal value in a case like this is minus infinity. We said that the problem is unbounded in a case like this. It's unbounded, which means the minimum does not exist, at least does not exist as a number. It exists if we allow infinity to be a number, which means that the objective function can be as negative as we want. For every m, we can always find a feasible point where the objective function is less than m, which is the formally correct definition of saying that the optimal value of p is minus infinity. So plus infinity if it's not feasible, minus infinity if it's feasible but unbounded. Then, given this, the problem of such an optimization problem is the constraint, usually. If we have no constraints, if we have to solve an optimization problem, we set the derivative to 0 if the function is differentiable, and we solve numerically derivative equal to 0 with Newton-Raphson, for example, and that gives an optimal point here. But the problem is the constraints here. So the classical trick is to introduce, not the trick, but the classical element of theory is to use the Lagrangian. So the Lagrangian consists in saying, I will replace the problem with constraints by what we can call here soft constraints or penalties. We add to the objective function a linear combination of the constraints here. So we replace this optimization problem, this f, by f of x plus sum of the lambda fi plus nu j hj, where lambda and nu are given numbers that are called the Lagrange multipliers. They're also called the dual variables. It means the same here. Now, this is where the tricks are important, the details are important. We have inequality constraint, less than 0 constraint here, and the multipliers that correspond to that must be non-zero, must be positive or 0. That's a constraint on them. The others, when we have equality, there is no constraint on them. This is the kind of details that make the thing complex. If an author chooses to put in the larger than 0 here, that will change the convention here. So all details depends on all details. That's why it's good to have one framework where the thing does not change here. So the Lagrange multiplier, lambda I and nu I, help us define an auxiliary optimization function, which is called the Lagrangian. And now if I solve the unconstrained optimization problem, unconstrained means I've removed the constraints here. I keep the implicit constraint, which is x being in the original domain of definition of the problem. That is what I call the unconstrained problem, which is also an optimization problem. It has an optimal value, which is plus infinity if it's not feasible, minus infinity if it's unbounded. So this value here depends on the values of the choices that I've made of the multipliers. For every choice of multiplier, there is a different objective function. There is a different result of the optimization problem. The result of this optimization problem, I call it the dual function, g of lambda and u. So to every combination of dual variables of Lagrange multipliers corresponds one value of the optimal unconstrained problem, and I call it this, which is now a function of the multipliers, is the dual function here. The dual function is not defined for every lambda nu, so the domain of definition of lambda nu is this, but plus we must have that this problem is bounded, and we call gamma the set of definition of the dual problem, which is the set of lambda nu such that this optimization problem is bounded. So the minimum is not minus infinity here. And then the dual problem is the maximum of the optimal value over all lambda nu in gamma here. That is the definition of the dual problem. Why does it make sense to call it the dual in this way? It would be a too long story to discuss. I think the important thing is to remember exactly this combination of max, mean, plus, minus, etc. here. So for every lambda nu, I can solve this optimal problem. I obtain g, and then I can maximize the optimal value of the unconstrained problem instead of minimizing the thing here. So there is some intuition. If I've removed some constraint, so the value I obtain is perhaps below the value of the original problem. So by maximizing, I try to make sure I remove the fact that I've removed the constraint here. And this is what is called duality when this happens. The optimal value of the dual problem is always less than or equal to the optimal value of the original problem, called the primal problem. That's always true. It's called the duality, weak duality result. And that's not very interesting in general. What we want is that there is equality. When there is not equality, the difference is called the duality gap, and we're interested in the case where it's 0 here. Incidentally, this result works even if the values are infinite. For example, if D is unbounded, if the dual problem is unbounded, then that means that this thing here is plus infinity, because that's a maximization problem, which means that P star is also equal to plus infinity, which means that the original problem is infeasible. So non-boundedness of the dual problem means infeasibility of the primal problem, which is a strong result per se, but that's what weak duality in this compact form implies here. But we're interested in solving exactly the original problem. The method that most often is used in all textbooks, they don't even mention it, but that's what they do. I use the Lagrangian. I solve the unconstrained problem. So I solve the unconstrained problem. That means I take values of lambda and nu. I compute the x star. Now the x star that solves the Lagrangian, the unconstrained problem, depends on lambda and nu. So the x star is optimal for the unconstrained problem for lambda and u. And then I look for special constraint on the Lagrange multiplier. The first constraint is that the solution I have obtained is feasible. So remember what we do. We have a constrained problem. I replace the constrained problem by an unconstrained problem. I remove all the constraints, but I modify the optimization function. That's this unconstrained problem here, which is this one here. That's the unconstrained problem that I have here, right? So if I solve this problem, of course, the point x, the optimal value of this, in general, is not feasible, does not constrain, does not satisfy those constraints because I've removed them. You'll try to minimize this linear sum of them, but it will not satisfy each of the h is equal to 0 and each of the f is non-negative. It will not satisfy this in general. The technique here consists in looking for a value of lambda and u such that the corresponding x satisfies all the constraints of the original problem. So we remove the constraints, introduce the Lagrange multiplier, solve the problem for every value of the Lagrange multiplier, and then look for the values of the Lagrange multiplier such that the resulting solution satisfies the original problem solution. That's the method that's invariably used, the very most frequently used method. In addition, we need to have what is called complementary slackness. It's a kind of ugliness. That complementary slackness means that if a Lagrange multiplier is positive, then the corresponding fi, which is a constraint with inequality here, must be true strictly, cannot be equal to 0 here. Oops. Right. So if we have equality in the inequality, the Lagrange multiplier must be positive. Otherwise, if we have strict inequality, the Lagrange multiplier must be 0 here. So essentially, this is saying if the constraint is binding here, the Lagrange multiplier must be non-trivial here. That's a technical thing that is necessary for the theory to work. So you verify this by inspection. You solve for every lambda the x. You look for lambda nu such that the x satisfies the original constraint. And then you look whether in addition, when that happens, these complementary slackness conditions are true. And if you're lucky, and if all of this works, you have solved your problem. You have solved the original optimization problem. The x star is a solution of the original problem, which was perhaps the only question of interest. In addition, we have that the lambda nu that we have are also the optimal solutions of the dual problem. And that, if that happens, that means the duality gap is 0, which means strong duality holds. So of course, this method works only in the cases where there is some hope for strong duality to work, which in practice works when the problem is convex. Strong duality holds for most convex problems, not all, but most. So that's, I would say, the method of choice. That's always, that's very often used. I will go quickly over some other methods that you may be confronted with. If instead of looking for solution of this unconstrained problem, we look for points that cancel the derivative, then that gives what is called the Karush-Kuhn-Tucker conditions, which is essentially the same. Instead of saying that we look for the optimal solution, then we simply look for a point that cancels the derivative. And this works if the problem is convex, not surprisingly, because we have seen that convex problem means local minima or global minima. And of course, the functions must have derivatives, otherwise this is moot. So the Karush-Tucker conditions, if they work, and this is in practice how we use the previous result, called the saddle point result, because that finding an optimal is replaced by solving an equation equal to 0, and you know how to do that with Newton-Raphson, for example, here. That works only if the problem is convex, because otherwise we find something that may be, there might be multiple local optima, for example. Here. I mentioned that all of those techniques work when strong duality holds when the duality gap is 0. And I said this is in practice true for convex problem, which is almost true. We need, in addition, what is called constraint qualification. Right? So constraint qualification, there are corner cases of convex problems where strong duality does not hold. But if one of those conditions work, which are called, there's one of so-called constraint qualifications. For example, this is one set of constraint qualifications. There is at least one feasible point. So if the problem is unfeasible, then we don't know what to say. Equality constraints are affine, and inequality constraints are either affine or are satisfied strictly by at least one feasible point. In practice, that may be hard to verify, except if for linear problems. For linear problems, essentially constraints qualification work because everything is affine. Affine means linear plus constant. And if a linear problem has at least one feasible problem, then strong duality holds. And strong duality means all the methods we've discussed work, which means you have a zoo of methods to solve the problem. You can solve it by looking for a saddle point, means looking for a solution of the unconstrained problem, and looking for values of the multipliers that make this solution satisfy the original problem. That's the saddle point solution. The variant of this is to use the Karush-Kuhn-Tucker condition. Or you can also compute the dual function, solve the maximization problem of the dual function. That will give you another solution. And all of those solutions give the same result if we are in this setting here. And in practice, if this always works whenever the functions are differentiable here. This is what it's saying. So in practice, when constraint qualification holds, all those methods I've discussed will work. Well, so that is, I would say, the recovery landing on constraint optimization to put the framework well in place. And because we want to apply the results on Lagrange multiplier interpreted as shadow prices. And since there are n different ways of defining your problem, each of the ways give different ways of stating this result here. So I'll use the Boyd and Vandenberg form, and this result comes as follows. Why do we do all this? Well, first to solve the problems very often with the saddle point method, and second, to obtain the interpretation of the Lagrange multipliers as shadow prices here. So assume I violate a bit what I just said a minute ago, but this is necessary for my discourse now. I assume that the constraints here are parameterized by some values u and v that can be interpreted as resources. So if I have to minimize a function of a state x, the state x satisfies this, and ui is a resource. For example, the resource corresponds to the fact that there is a maximum current on the line or a maximum power flow on the line here. If I have a better line, I can increase the power flow constraint, but I need a thicker line with more copper. So I need a better resource here. This is what this is trying to capture. And the question we ask is, how does the optimal value of this depend on the value of of those u and v here? Then there is this result that I'm summarizing results that are all in Vandenberg's book. By the way, this book is freely available online, so I recommend that you download the book if you want to verify or more details. The result is that the derivative of the cost here, so C is the cost of the optimal value of this problem as a function of u and v, of all the parameters u and v here. Then the derivative of C with respect to ui, so the ith element of this constraint here, is minus the Lagrange multiplier associated with this constraint, and similarly here with mu j. That's the result here. Now why does it correspond to a shadow price? Well, here's the explanation. If you take the ith constraint here, you interpret it as a resource and assume that you add epsilon I to the ith constraint. So ui is increased by epsilon. Then somebody comes and offers to us to buy this increase, epsilon, at a price less than lambda I. So I've solved the problem. I have the optimal Lagrange multiplier, lambda I, which lambda I should be lambda I star here. Now somebody comes and say, I can change your problem. I add more resources and put your power line, power flow constraints. I can increase it by some epsilon, but you need to pay lambda I times epsilon here. You need to pay something. Now, if the cost is less than lambda I, then we would take it because the increase in benefit will be minus lambda I. So my reduction of cost will be approximately minus lambda I epsilon. Since I've paid less than lambda I epsilon, I benefit here. Right? So if somebody comes and say, I have a way to improve your grid, it will cost you so much, less than lambda I, do you take it? I say, yes, I take it, because by having this increase here, my cost decreases by more than what I pay. And vice versa. If somebody comes and say, I want to improve, but it costs more than lambda I should not do it, because at the end, I pay more than I benefit. So we can interpret that by saying, well, that's the hidden or shadow cost of this resource, means that by having those constraints, it has an impact on what I pay. And this impact can be quantified by exactly the shadow price here, this Lagrange multiplier here. Back to our OPF problem. If our OPF problem satisfies all of this, which means if it is convex and satisfies constraint qualification, which is true if I have linearized the problem, but is not true for the original OPF problem. So for the linearized problem, if I can apply this, and then I can ask the question, what is the locational marginal price, which is the increase in price on node 1, if I increase the demand at one of the nodes here. The demand at a node, in our toy example, was L1. That's the load demand at node 1 here. And now the question is, how much will the total cost of operating my grid will increase if I increase lambda 1 by some epsilon? Then the answer is dc over dl1 by the formula of total derivative is the sum of the derivative of ui over of the cost of with respect to the ui themselves may depend on L1. If you remember the examples we had, no, it's not here. I'll show it in a second. Here are the constraints that are, here's my OPF problem, DC OPF with this linearization. Here is one constraint here. So the variables, the X are the thetas and the Gs, and here is one constraint, and L1, L2, L3 are parameters of the constraint. This is my U here. So if I want to apply this formula, the derivative of the cost with respect to dl1 is the sum of the derivative of the cost with respect to U multiplied by the derivative of U with respect to L1. It's the formula of total derivative. And the derivative of the cost with respect to U1 is minus lambda I, or minus nu j with respect to nu j. So this is how the locational marginal prices can be obtained immediately from solving the problem. Now, any solver that solves the optimization problem will give you the Lagrange multipliers. Here is the solution of the Lagrange multipliers here. Here are all the Lagrange multipliers. They correspond to each of the constraints. For example, this is the constraint on, we see that the Lagrange multipliers that are non-zero are the only ones where the constraints are binding. We see that the constraint on P23, the line here is saturated here, and G1, that means the constraint on G1, which is here, is saturated here. So we have two saturated constraints that correspond to two non-zero Lagrange multipliers. If I apply the method, I obtain exactly this marginal costs, and this is why you will pay more in one city of Europe than another one for on the real-time market for electricity, for example. Voilà, I think I will conclude this. There are 2 little quiz, but leave it to, I will post the solutions. You will be able to see them online. This concludes our very, very simple introduction to OPF. Next week, we will do a bit more. What we have seen is that the problem is essentially, is a central problem in grid management, planning, operation, control. We've seen 2 simple methods for solving it, DCOPF and SLP, that both rely on linearization of the problem. Because that problem is so important, as you can imagine, there's a whole literature that is trying to solve it better. There are, for example, what's so-called convex relaxation that are used a lot. There are convex formulation, which is different from convex relaxation, that slightly modify the problem but work only for radial grids. This one works only if there is no shunt element. There are linear approximations that works only for radial grids that are more accurate than DCOPF, but do not work if there are loops in the topology, like in the grid I've shown. And there are other iterative schemes that are working better for 3-phase grid, etc. So that's another topic. And as I understand, some of you may be working with in some projects on solving this OPF problem. Voilà, that's all for this week. There is a quiz to be done online before starting the lab. And next week, we will complexify a bit the problem by adding uncertainty to the variables that we have observed.